Okay, so today we're continuing our study of linear algebra, and we're moving to a fundamentally different topic than solving ax equals b. There are some relations, but this topic is the beginning of a new portion of linear algebra on eigenvalues, and in particular to data science majors, the singular value decomposition. So that's where we're going. So this is actually taken from the Strang linear algebra book. So this is 6.1 and Strang, Gilbert Strang's linear algebra book. Okay. So previously, we were looking at systems of equations. We were looking at matrices that were m by n. Now we're going to focus on square matrices, so n by n matrices. So we will focus now on square matrices. Square n by n matrices. Okay, and each square matrix is going to have what's called a determinant. So each square matrix I'll say is associated with a single number called the determinant. And this number, it contains a surprising amount of information about the matrix in question. It will give us information about the invertibility of a matrix, which is how we will define what it means for a matrix to be singular, which we haven't gotten to yet. It will also tell us a way for solving for what are called the eigenvalues of a matrix, which will come next lecture. So it's very important in relation to eigenvalues to me. It's also related to how a matrix, if you recall, a matrix times a vector will stretch and maybe rotate a vector in space. And there is a great video on determinants by 3 Blue 1 Brown. It gives a geometric interpretation of volume with respect to the determinant. I'm not going to focus on that because that's not our end goal. Our end goal is eigenvalues and eventually singular values. So just keep in mind, you should probably watch that video that I posted on Blackboard. So notation for the determinant of a matrix, I'll use two different notations. And for matrix A, I'll say DETA, or I'll use vertical bars A to represent this number, the determinant of a matrix. Okay, so let's start with a few properties. More specifically, 3 properties. So the 3 basic properties of the determinant. So number 1, the determinant of the identity matrix is equal to 1. Or using this bar notation for example, okay, so that's property 1. determinant of the identity is equal to 1. Property 2, if you exchange rows, the sign of the determinant changes. So exchanging 2 rows changes the sign. Of the determinant. So, for example, we know that the determinant of the 2 by 2 identity matrix is 1. So we know that the determinant of the 2 by 2 permutation matrix is going to be -1, because we just interchanged those rows. Okay. And then property 3, well, this is, I should probably break property 3 up into 2 separate parts. So, but I'll say that, no, I'll have to do it in 2 separate parts. So 3a, so if we multiply a row by a scalar, so multiplying a row by alpha will result, I'll say multiplying a row of matrix A by some scalar alpha will result in a matrix with determinant alpha times the determinant of the original matrix. So, for example, alpha times A, alpha times B, C, and D, the determinant of that matrix is equal to alpha times the determinant of A, B, C, and D. Okay. Only one row. Okay. One row at a time. All right, 3b. What was that one? That was oh. So I think the best way to write this is to say like this. I'll just give a 2 by 2 example. A plus A prime, B plus B prime on a given row, C and D. This is equal to the determinant of A, B, C, D plus the determinant of A prime, B prime, C, and D. So adding onto each entry of a given row, you will be able to form a new matrix like this, and the determinant of this sum is the determinant of the original matrix. Basically, what I'm trying to get at here is that the determinant is a linear function in each row. So if you multiply by alpha and add A prime and B prime, or any number of numbers to a given row, it's going to act like a linear function.
Do A prime and B prime hold any special relationship to A and B, or are they just constants?
They're just constants.
Okay.
Yeah,
cool.
these could be any numbers.
Gotcha.
Okay. All right, so these are the basic properties. So make sure you have these written down because we're going to use these to derive the next 4 properties of the determinant. Okay. So determinant identity is 1. If you exchange 2 rows, the sign changes. If you multiply a row by a scalar, you have scalar times the determinant. If you add to each entry of the row, then we have sum of determinants, but this is only per row, or 1 row at a time. Okay. If you also added to this row, then you would have a 3rd matrix over here. You'd split it up 1 at a time and just think of this as the base property. So these are the basic properties. Okay. All right, so now the, maybe I should say the other properties that we can derive using the basic ones. All right, so we're on property 4. And this says that if 2 rows are equal, then the determinant of the matrix is equal to 0. So if 2 rows are equal, the determinant is 0. Okay. Now, why would this be true? Just using the basic properties. So if determinant of A is equal to some number, I don't know, Q or something. So if determinant of A is equal to Q, and row I and row J are equal, interchanging rows, or interchanging these rows, changes the sign. But they are the same matrices. These are the same matrices. So what that says is that negative Q is equal to Q, which means that Q is 0. Right, like determinant of A, B, C. So that's the proof more or less, but just to see with the case of 2. So if you have a matrix like this, and you take the determinant and it's equal to Q, then if you interchange these rows, you get the same matrix back, right? But now, since you interchange the rows, the sign flipped. But these are the same matrix. So that means that Q must equal negative Q. And the only number that satisfies that is 0. Okay. All right, property 5. subtracting alpha times row I from row K does not change the determinant. Okay. So if you take a multiple of a row and then subtract it from another row, it does not change the determinant. And that's a mixture of 3A and 3B. Right, so maybe just for example, let's see if we can verify it for the 2 by 2 case. So suppose this has, we're taking the determinant here, and suppose that determinant is equal to like R or something, some number R. I didn't use K because I used row K here, but whatever. So suppose that equals R. So then if we multiply a row and then subtract it from another row, so what is this going to be? So we claim that this is equal to A, B, C minus alpha times A, and then say, what is going to be D minus alpha times B. Well, then we can apply this rule here. It's like adding, right? So we have A, B, C, D, plus, and then the determinant of A, B, and then minus alpha A minus alpha B. You see that? It's like that and that, right? That's just 3B. But then this is like, so we still have this determinant here. But then we can use property 3A and just take that alpha out, that minus alpha. Oh, but then here, this matrix has two identical rows, right? So then that's going to have determinant 0, and we're just left with the determinant of A, B, C, D. So yes, that determinant equals that determinant, nothing changed, we're good. So we can subtract off any multiple of a row from another row, doesn't change the determinant. Okay, now I should probably say something about determinant of A being 0. Determinant of A is 0. We say that A is singular. Okay, A is singular when the determinant is 0. Okay, and then finally, well, not finally, we have two more. So this is what, rule 6. The determinant of an upper triangular matrix is, say, what did I use for my notation? D11 times D22 times times D n. It's a 2 right there. And this is the product of the diagonals. So you have D11, D22, Dn, and these are all zeros over here, and then you don't know what these entries are. This is the upper triangular matrix. It's the determinant is just the product of the diagonals, or in other words, the product of the pivots. And when you do Gauss-Jordan elimination. Remember, the pivot is what you use to zero out everything below it. It doesn't have to be a 1, but as long as everything below it is 0, it's a pivot. So pivot, you can use that to zero out everything below it. So why would this formula hold? Well, this goes back to a combination of rules. So this is combination of rules 3a and rule 1. So we know the determinant of the identity matrix is 1, and we know that we can factor out alphas or constants and change the determinant by a constant. So if we were to make this matrix here the identity, well, maybe let's look at an example like a 2 by 2 case, because we need the formula for the 2 by 2 case anyhow. Okay, so how can we verify this formula? So this is not an upper triangular form. We need to make C equal to 0. So something times A plus C is equal to 0, which means that alpha is equal to C over A, or minus C over A, right? So if we multiply A times minus C over A and then add it there, that'll be a 0. So let's multiply that row and add it to this row by that amount. So A, B, and then what do? C minus C over A times A. And then I need to make this bigger. D minus C over A times A. Okay, so that'll be 0. And then we have D minus C over A times A. Well, it's just minus C at that point, right? But now our goal is to get the identity, because we know that the determinant of the identity matrix is 1. So let's go ahead and factor out D minus C from this row alone. And we know that by property 3a, it's going to be D minus C times the determinant of AB 0, 1. Actually, before we even do that, let's just use this as a pivot to get rid of the b above it. So if we multiply this row by, what is it going to be? Negative b over d minus c, and then add to the top row, what do we get? So that's a 0, so a stays the same. And then we'll have b minus b over d minus c times d minus c, 0, d minus c. So this obviously becomes minus b, that becomes a 0. So then we'll have, what is this going to be? A 0, 0, d minus c. Did I do this right? Where am I going wrong here? If you're confused on what I'm trying to get at, I'm trying to get at a bunch of scalars times the identity. Because then the determinant of the identity is just 1, and then it's going to be all the scalars that we can factor out. Let's see. Because now it looks like it's a times that row, d minus c times that row, so it looks like it's going to be a times d minus c is going to be equal to the determinant, but I know that's not the case. A times d minus c times b. Well, it's almost there. I'm just missing one thing. A times d minus c minus 1 second. This is where I need more room. I'm going to start over from scratch right here, just using the basic properties. I'm going to make it upper triangular, like this. And this will be A, B, 0, D minus. So, oh, that's where I made my silly mistake. There. That should have been a B, C over A times B, minus C over A times B. That was my silly mistake. Because I'm taking a multiple of the first row and adding it to and subtracting it from the second row. The multiple I chose was C minus A times this row. So I'll get a 0 there, but then I have this here. Yeah, that was I have an A there instead of a B. So let's just erase this bad work and keep this. So to get from there to there, I took C minus C over A times row 1, or C over A times row 1 subtracted from row 2. So that's how I get this new matrix, which I'm allowed to do. That doesn't change the determinant. So I get a 0 there. And now I want to make that a 0 above it. So in order to do that, I take all of this over itself, and you can see that it's not difficult to do this. right? So I multiply this row by B over D minus D over A B. I multiply that row by that, and I subtract it from the top row, and that becomes a 0. Right? Because this times this is just B, and then that B minus B goes away. That times 0 is just 0, so there's nothing, no change to A. And then we know that we can take out scalars from rows. So this would be A times, what is it? A times 1, 0, 0, D minus C over A times B. Okay. And then now we can take out that scalar from that row, and we get A times D minus C over A times B times the determinant of the identity. We know that that's just equal to 1. So then here, we get A times D, and then A times this is just CB. So A times D minus C times B. Okay. And we see that basically the reason why this is true is that when we take this upper triangular matrix and we start zeroing out everything above the pivots, what you get is that you get eventually to where there's all zeros and factors of these D's in such a way that when you factor them out using property 3A, it turns out that it becomes just the product of the pivots times the identity matrix. And the determinant of identity is 1, so you're just left with the pivots. And that's what's happening here. It's just the product of the pivots. Now, this is actually a special case right here. So we actually did more than just show that, see, this was the upper triangular form right here, A times this. So we verified it in this case. But we also gave a general formula for a 2x2 matrix. So the determinant of a 2x2 matrix is easy to calculate. A, D minus CB. So that's easy to calculate now for a 2x2 matrices. Okay. All right, so this actually leads us to an algorithm to find the determinant. So what else have we learned about determinants from property 6? The steps to compute the determinants for any reasonable algorithm is to put A, or change A, put A into upper triangular form. Yeah, I'll just say upper triangular form. Then take the product of the diagonals. Now, remember from our previous lecture that if any one of the pivots becomes 0, and so you can exchange rows in Gauss-Jordan elimination, nothing changes. But the goal was to get a bunch of 1s on the diagonal. And if you were to get a 0, Like once you finish the process and you had a row of zeros or there was 0 on the diagonal, you could not invert it, right? That's one thing that we learned. So in particular, what this says is that if one of those diagonals is 0, you can't invert it because, well, that's what we learned last time. But if one of the diagonals is 0, once it's in upward triangular form via Gauss-Jordan elimination, once that's the case, the determinant is 0. So, so the determinant of A equals 0 is the same thing as saying that A is not invertible. And the name that we gave this earlier for both of these now will be that A is singular. Okay. Another way to see this is with the next property. Property 7. The determinant of A is equal to the determinant of A transpose. Okay, now, so earlier when, I forget which property it was. So this will be our final property, but what is this saying? Well, first, let's make an observation from before, from previous. So we know that adding multiples of rows together does not change the determinant. Okay. We also know if there's ever a row of zeros, the determinant doesn't change. So what that means is that if 2 rows are the same, the determinant is 0, which again means it's singular, means that it's not invertible. But what this is really saying is that if the rows of A, and we'll come back to property 7 in a second, but first let's just note this. If the rows of A are not linearly independent, then A is singular. Right, because if adding and subtracting multiples of rows together doesn't change the determinant, and if there's ever a row of zeros, then the determinant is equal to 0, then if they're not linearly independent, then one of the rows can be written as a combination of adding and subtracting multiples of the other rows, which means that we can get rid of it and make that row 0, which means the determinant of A is 0, which means it's singular, which means it's not invertible. Okay. Now, what does property 7 say? Well, the determinant of A is equal to the determinant of A transpose. The determinant of A transpose, the columns of A then become the rows of A transpose. So if the rows in A are not linearly independent, then it's going to be singular. I mean, the rows in A transpose are not linearly independent, then it's going to be singular. The columns in A will not be linearly independent if these equal, right? So we can say the same can be said for the columns, which we already talked about. When we were talking about invertibility, that says columns, when we were talking about invertibility, we spoke about the columns of A being linearly independent, right, in order for it to be invertible. If they are not linearly independent, then it wasn't invertible. That's also because of this. So determinants are important because they, one, tell us, well, two things. The two important takeaways. They're a test for invertibility. Okay, so that's, if the determinant is 0, then we can't invert it. They also say that if the determinant is non-zero, then these are biconditional statements, by the way. If the determinant is non-zero, then we can invert it. But then also, this formula here tells us how to compute the determinant, which will be important when we start talking about eigenvalues. Now, I would like for you to do from section 5.1. I know I wasn't going to ask for very many more homeworks, if any at all, but I really think it's important that you do these. Or at least like attempt them. So from this section 6.1 and Strang, do 1 through 9. And (13, 14, and 23. And you can turn this in Friday. You know, everyone should have a PDF of this book now. So I'm going to go ahead and stop this lecture here, and then we can talk about the projects.